So, ladies and gentlemen, dear Vanessa, Vice President, Personnel and Leadership, if I'm correct. Dear Catherine, Professor De Wolf, dear colleagues, and again, ladies and gentlemen, welcome to this inaugural lecture by Professor Catherine De Wolf. So it's a pleasure to introduce to you a new faculty member of the Department Civil, Environmental and Geomatic Engineering. My name is Paolo Burlando, and I'm the department head of this department. Professor Catherine De Wolf joined our department in September 2021 as assistant professor for circular engineering for architecture. And these two disciplines, engineering and architecture, particularly civil engineering, have been present in her academic life since her Bachelor of Science and Master of Science. She completed them at the Free University of Brussels, obtaining a double degree in civil engineering and architecture. She then moved to overseas, precisely to MIT, to Boston, where she obtained her second Master of Science and her PhD, both in building technology at the Department of Architecture. And so one could almost say that in her arteries and veins, a mixture of engineering and architecture blood flows. And this has probably also inspired the name of her chair, Circular Engineering for Architecture. So before joining ETH, she worked at the PFL as a postdoc at the Structural Exploration Lab, and more recently as assistant professor at the Technical University in Delft in the Netherlands in the field of design and construction management. She also cooperated closely with industry and the private sector, for instance, with the leading design companies Arup and Thornton Tomasetti, to build a database of embodied carbon in buildings. Or with Elliott and Maximum on reusing the glass of the well-known Centre Pompidou in Paris. Her research is very contemporary. Circularity is a word which we often hear, not only in science, but also in everyday life. And her research contributes to addressing pressing societal questions, for instance, decarbonization of society. In this respect, it's worth to mention that she was one of the initiators of the Structural Engineers 2050 Commitment Initiative with the Carbon Leadership Forum, which aims to understand, reduce, and ultimately eliminate embodied carbon in all the projects designed by structural engineers. So the collaboration with industry is key for her research, but also an inspiration and a basis for her teaching. Another distinctive character of her research is the pervasive use of digital technologies, and you will certainly see something tonight. Combining collaboration with industry and digitalization allows the teaching digitalization for circular construction in a very handy way, and I'm sure the students will appreciate, if they didn't already appreciate, in the past semester. So at her chair, she develops research on matching reuse architectural materials and projects through digitalization for circularity. I'm sure she will explain all of this in her lecture. Research in digital technologies and circular strategies and promoting their adoption in industry can lead to using buildings as material mines in place of scarce and endangered natural resources on our planet. So, Catherine, we are eager to learn about the complex and interdisciplinary nature of your work, and the floor is yours.
Thank you, Paolo, for this very kind introduction. Dear colleagues, dear friends and family, welcome to my inaugural lecture. I'm very happy to be here in person in front of you today. Now, the title of my lecture, This is Not a Pipe, is referring to this painting from the Belgian surrealist painter René Magritte, who really challenged us to change our view of the world. Now, my lab, the Circular Engineering for Architecture Lab, or CEA Lab, has two things in common with René Magritte, other than the fact that I'm also Belgian. First, we like to transform pipes that we find in buildings into something else. And second, we want you to change your view of the world, to look at the world differently, and especially at buildings. Now, you'll have to wait a few more slides before I show you what a pipe can be when it's not a pipe. But a building that's famous for its pipes is the Centre Pompidou in Paris, in France. So Renzo Piano and Richard Rogers designed it in a way that all of the surface equipment would be shown on the outside. So the inner workings of the buildings are shown on the outside. So here you see pipes on this side of the building for water, ventilation, and so on. And on this side of the building, you see the circulation. So you see this beautifully bent glass that is covering the hallways and the escalators, which are famously known as the caterpillar of the Centre Pompidou. Now, I had the chance to work for Elliott, who was the engineering company responsible for the renovation of this facade. And we had to replace the glass, the beautifully bent glass, because of changing security norms. So we went on a mission to find a new home for the glass. And luckily, we found the young designer firm called Maximum, who had a client that needed this bent glass for this project right at the same time that we were disassembling the glass. So the caterpillar became a butterfly. Now, why do I care so much about the reuse of this glass, or the reuse of pipes, or the reuse of other building materials in buildings? Well, as actors of the construction sector, we have a crucial role to play in the climate crisis. Buildings are responsible for about 39% of all of our greenhouse gases, and we've done considerable progress in how to reduce operational emissions, so that's related to the use of the building, so think of heating, cooling, ventilation, lighting, and so on. But the use phase of a building is only part of the whole life cycle of a building. When you look at the full life cycle, you also have to deal with embodied emissions, which is related to material extraction, production of building materials, bringing them to the sites, construction, maintenance, and end of life, which is usually demolition. It's not only about the greenhouse gas emissions, it's also about resource depletion. We're depleting a lot of resources for construction. For example, we mine about 40 billion tons of sand per year just because desert sand is too fine for construction. This creates a huge biodiversity problem. Sand mafias are created as well, so we need to deal with this. We're also creating a lot of waste. Here is the King Dome in Seattle that was demolished only 26 years after its construction. And this building was designed to last for 1,000 years. So in Europe, about 30% of all of our waste comes from the construction and demolition sector, and this number is even higher in Switzerland. So what's wrong with the construction industry? We build in what we call a linear economy model. So we extract raw materials, we produce building materials, we use them, and then we dispose of them. What we need is a paradigm shift towards a circular economy model, in which we use only renewable resources, in which we use our buildings as long as possible, in which we repair our buildings, in which we reuse our building components, and if all else fails, we recycle them. Now let me pause a little bit on the difference between recycling and reuse. So when you recycle a material, you take the component and take energy to bring this component back to its raw materials. Think of wood chips, of melted steel, of crushed concrete aggregates. On the contrary, when you reuse a building material, you keep the component as it is. So think of reusing a wooden window frame, or a steel beam, or a concrete slab. Now, our lab is focusing mostly on reuse, and here's why. This is the Maison des Peuples, designed by Victor Horta, a Belgian Art Nouveau architect. And this building was disassembled in 1965. People thought this structure was so beautiful that they stored this structure for 35 years until they could find a new home for the structure, the Hortazaal in Antwerp. Now, if we would have recycled this structure, we would have used energy to melt back down the structure to its raw material. This would have probably downcycled the material. And wouldn't it have been a shame to lose all of the effort, the labor, the energy that went into making this beautiful structure? Now, you're probably thinking, well, we can't afford to store our materials for 35 years, right? Well, you're totally right. We have to align the moment when we disassemble a building with the moment when we reuse those materials in a new building. And that's what we did with the Centre Pompidou, where we had to disassemble the materials at the same time when the new client needed them. Now, it's relatively rare today that the end of life of one building aligns with the start of life of another building. So to be able to move towards circular construction on a large scale, and not just for iconic buildings like the Centre Pompidou, like the Maison des Peuples, we need 5 things. First, we need data. Data on how, when, where materials will become available for reuse. Second, we need detection methods. Once we have identified a building that will be demolished, we need to detect which materials are in the building and in what condition they are. Third, we need smart ways to disassemble a building. We need it to be cheaper than demolishing. And fourth, once we have disassembled a building, we need to distribute those elements by giving them an identity, by tracking, tracing, and trading them. And fifth, we need to completely change the way we design and fabricate our buildings. Now, these are also the 5 steps of our research at the CEA lab that I will talk about today. So our question is, could digital innovation help us disassemble a building and reuse its building materials in a much faster, better, and cheaper way than ever before? Because only then will circular construction be competitive enough so that we can abandon the linear model. Could digital technologies help us save not only the glass of the Centre Pompidou, but also all materials of other buildings worldwide? Could digital technologies help us use buildings instead of the earth as a mine? Could buildings become material mines, material depots, material banks? Now, the construction industry has been famously known to be slow in adopting digital innovation, even though digital innovation is everywhere and growing. We've used blockchain technology in about 20% of traditional banks. We use robotic manufacturing everywhere in the car industry. We use artificial intelligence or AI literally everywhere, from online marketplaces like Amazon to Tinder, to dating platforms like Tinder. So we were wondering, could these digital technologies help us bring the construction industry towards circularity? Could these digital technologies help us face the biggest challenge that construction is facing today, this transition to a circular economy? And that's exactly what the CEA lab does. We explore those digital technologies that are used a lot in other sectors. We bring them to the construction sector to see whether this can improve our circularity. So to do so, we had a flagship project that we worked on in the last few months, where we actually disassembled the building and reused the materials and tested all of those digital technologies on this flagship project. And we did this together with Materium, one of the prominent reuse actors in Geneva, where we disassembled this building here that you see on the left. That was an old car warehouse in Geneva. And with these timber beams, we built a dome-shaped greenhouse in Zurich. Now, as you've seen, our research is divided in 5 topics, and the first is data that we need to predict when materials will become available for reuse. Now, when I was doing my PhD at MIT, I was already working a lot with data. I created the database of embodied quantity outputs, or DECO, which is a database that collects structural material quantities from structural engineering companies such as Arup, Thornton Tomasetti, SOM, and so on, so that we could compute the embodied carbon of these building structures. Now, one interesting thing that I learned from here is these are the type of graphs that you can see on deco.mit.edu. So here on the y-axis, you can see the structural material quantities in kilograms of material per square meter of floor area. On the x-axis, you can see the number of floors. So that you see here on this graph that the higher you build, the more you need materials per square meter of floor area. This is interesting because this was confirming what Fazlur Khan, the famous skyscraper architect and engineer, already told us in the 80s, that we pay a premium for height. The higher you build, the more you need to take into account other loads like wind loads, for example. Another thing I learned from my database was that the Beijing Olympic Stadium, also known as the Bird's Nest, uses more than 10 times the embodied carbon compared to the London Olympic Stadium. Now that's interesting because the London Olympic Stadium was built 4 years later with a change of mindsets, right? Sustainability became much more important, and they set this right at the design stage as a goal. So they used lower carbon concrete mixes. They reused some materials from a gas pipeline construction site nearby. They also designed the stadium to be partially disassembled after the games. And so you see that if you put the right goals at the design stage, you can really improve your impact on the environment as an architect, as an engineer, as a contractor. Now, this led to the Structural Engineers 2050 commitment, which Paolo mentioned earlier, which is a commitment where structural engineers sign up to share data about their structures and lower their embodied carbon each year a bit more. Now then, I did my postdoc at EPFL, where I upscaled this research on the urban scale, where I looked at the city of Geneva. So we looked at embodied carbon emissions throughout time. So we went into the archives until 1850. And so we mapped the embodied carbon and construction/demolition from 1850 till today. This is very interesting because the past can teach us a lot about why buildings are getting demolished or constructed. Now at ETH Zurich, at the CEA lab, we look not only at the past, but we also try to look at the future. We try to predict when buildings will become available for reuse. To do so, we use AI, artificial intelligence, and more specifically machine learning, to predict when these materials will become available. We apply big data analytics on various data sources that can help us detect demolition sites or renovation projects and so on. So algorithms can identify patterns in the data to help us make those predictions. So for example, here you see the machine learning work of one of my PhD students on Google Street View data. So we have a lot of images from facades on Google Street View, and so we labeled these images with an online annotator so that we could train the model. We explored instance segmentation to identify reusable components. We used a mask region-based convolutional neural network framework for computer vision tasks to detect objects such as windows that are available for reuse from those images of those facades. So as I mentioned, we use various data sources. Google Street View is one of them. There are many, many images for many cities that are available that we can learn from, but we combine this also with cadastral data. Lots of cities also have geographical information system maps, GIS data, and the city of Zurich, we're quite lucky here, has a lot of data. So here you see a map that we're able to draw with, in orange, the residential buildings, and in white, the non-residential buildings. Here, the different construction periods. So green is from the 1800s, orange is from the 1900s, and then red is after 2000. Here you see a map also with more precise construction periods for residential buildings. So that's also very crucial information. We also can gather a lot of information these days from social media. That's also super interesting for us to work with. From public records, we have lots of archives and other data that the city of Zurich makes available to everyone. Another thing that's very interesting is using data from insurance companies, because they also try to predict the future. And then, of course, data that comes from our colleagues. The Computer Vision Lab, for example, here at ETH Zurich, has developed this project called Varsity, where they made a 3D model of the city of Zurich based on aerial data, based on public webcams, and so on. We're also quite lucky here that this photographer in Zurich that took some pictures of lots of buildings in the 20th century with the addresses, the exact addresses of all of those buildings, so we can actually compare them to what they've become today. And this helps us also to understand how buildings evolve over time. Now, once we've predicted which buildings are available for reuse, we also need to check whether the materials are actually suitable for reuse. So we also use machine learning for this. We do this work with Politecnico di Milano, where we define different evaluation metrics and use image classification to define which structural elements can be reused or not, based on things like, are they corroded, damaged, distorted, are the connection bolted or welded, and so on. So machine learning really shows, and computer vision in particular, shows really promising potential for collecting data visually on building-specific characteristics that are useful for reuse. All right, so once we've identified buildings that are about to be demolished, we zoom in onto the building, and we try to detect which materials we can reuse. So we use a lot of digital technologies in the field of reality capture, and this goes from simple photos from our phone cameras to photos taken with autonomous devices like drones. Or we also use webcams on our hard hats that are connected to a software that reads where you're walking in the building throughout your scanning. So here you see one of my PhD students using the OpenSpace.ai software to do so in the building in Geneva that we disassembled. So then we use photogrammetry to process the images into estimated point clouds. So these are point clouds from the building in Geneva that we disassembled. What's interesting is that you always have to be on the spot when you want to have some buildings salvaged from, some material salvaged from a building. The building, when they are set for demolition, this was the old Fiat, Lancia, and Alfa Romeo importer, and this building became obsolete. So they're going to demolish it for something more tall, probably. And usually when the buildings are obsolete, they give them to the police so that the police can do some training and explode some doors or walls and so on to break into a building. And then after the police is done, then there is my time window before the demolition starts where I can do my research and I have access to the building and I can salvage any material that I want. So that's usually how our research works. We also scan buildings that are not so soon set for demolition, but using light detection and ranging, so LiDAR scanning techniques. So we tested this full-scale LiDAR scanner that we borrowed from the Design++, so the Center for Augmented Computational Design in Architecture, Engineering, and Construction that we collaborate a lot with. And we scanned the DFAB house at the Nest building in EMPA. So the Nest building is a building at EMPA where you can test some of our research. So we actually get to build units, entire units, test our research on a scale 1:1. And my colleagues from the National Competence Center of Research for Digital Fabrication, the DFAB NCCR, have built this DFAB house in the Nest EMPA building. And this is really interesting for us because they have very detailed data on that building because it was digitally fabricated, right? So we can easily compare our models, our point clouds and our scannings and so on with the actual reality. So this is the results of our scans. All right, so we also take a look at mobile equipment, industry standard LiDAR, digitization systems, and so on. Here is another LiDAR scan of the Huber pavilions. Maybe those of you who've been to the Hungerberg campus have seen them. They're about to be disassembled, and we scanned them beforehand. We also tested some apps on our smartphones. This is me scanning the building in Geneva with my smartphone that has some LiDAR capabilities and some LiDAR using apps on the phone, just because we think it's important to also test mobile-based, accessible equipment, right? The LiDAR scanner I showed you in the DFAB house is super expensive, so we cannot expect all of the reuse actors to own such an equipment. Of course, the smartphone LiDAR scanning is a little bit less accurate, so we have to evaluate what we can do for reuse with the scans. So next ones, we have the point clouds. This is very unstructured data in a way, so we need a method to make a BIM model, a building information model, out of this unsorted scanning data. So we need to identify the types and forms of building elements on site. So we developed several scan-to-BIM methodologies to do so. We try to detect the beams and columns based on point density, on statistics, on matching, and so on. We also try to identify how the elements are connected to see how recoverable those elements are. So in the future, we're planning to collaborate with the Robotic Systems Lab in the Mechanical Engineering department here at ETH to apply their work on combining LiDAR scanning with their beautiful animal robot that is walking around the campus there, making a digital twin of the building. And so I think this is a very interesting and promising research area where we combine our research on circular economy with their research on robotics so that we can make a BIM model for reuse in a completely autonomous way. So once we have the geometric shape of the building components into our BIM model, we also use image-driven data intelligence to augment the BIM elements with reuse relevant information. So we need to know not only the geometry, but also the type of materials, right? What conditions are the materials in? So here you see, for example, 2D and 3D computer vision techniques that are applied to classify images captured on site into material classes, masonry, steel, concrete, wood, and so on. We also want to identify what condition the materials is in. So our work is based on traditional feature-based algorithms and on state-of-the-art convolutional neural networks. So these scan-to-BIM technologies enable us to make an inventory of the beams that we disassembled. So we have information like the type of wood, the type of, the condition in which the wood is, the dimension of the element, and so on. So based on the point clouds that we had of the old car warehouse and on the computer vision techniques that we applied, we can find a BIM, we can define or make a BIM model of a building that doesn't have a BIM model, that doesn't have information, and we can make an inventory, which is very useful in the design stage, you'll see later. We also plan to collaborate more with Design++ on using virtual reality to walk throughout a building and have some information about the demolition site that you are walking through. All right, so once you have scanned the building, made your BIM model, made the inventory of your building materials, you can actually start disassembling it, right? But disassembling is much more challenging than demolishing a building. You need more care, more skills, sometimes more time. And I like to teach my students hands-on what it means to be on a demolition site, what it means to disassemble a building. And so this is one of the courses that I co-organized with the East Lab at EPFL on the disassembly of the old tram depot in Bern, where we went on site. We co-organized this also with Rotor, one of the major Belgian reuse actors, together with Losinger Marazzi, the Swiss daughter firm of the big industrial group Bouygues, who gave us access to this old tram depot from 1906. We had no information about this tram depot until one guy randomly walked by our deconstruction site and asked us, "What are you doing?" And we said, "Well, we're disassembling this building for reuse and so on." And he said, "Ah, but that's super cool. I'm a big fan of the tram depot. I have the original blueprints from 1906 at home." So apparently people own blueprints from public buildings at their home. So this shows really how random information of buildings, of today's building stock is. Here you see our students trying to disassemble the beautiful structure. We hope to reuse this structure in another building. It's very challenging, and they learn a lot about what is a good way of disassembling on site. This is me also cutting a steel beam. This is in the car warehouse in Geneva. And these steel beams were welded, unfortunately, so we had to cut them if we want to reuse them. And it's a very sensorial experience because we used battery power tools. And after each steel beam that we cut, we had to recharge our batteries. So it shows us really hands-on how much energy you need to cut steel beams. And it really convinced us to make reversible connections in our new designs and to go for bolted connections, for example. This is us chilling on one of the steel beams just before our lunch break. We're just a little bit less up high in the air than the iron workers in New York City. But nevertheless, having the time of our lives, disassembling a building. This is me disassembling the famous pipe I told you about. So I knew exactly what I was going to do with the pipe. But you'll have to wait a few more slides to discover what I did with the pipe. All right, we also disassembled some OSB boards. Lots of them, actually. Lots of timber beams that were in perfect condition. The timber beams were way less challenging to disassemble because they were just screwed together. This, again, convinces us that dry connections are really the way to go. Then the next challenge is the transport of those materials. We had to transport those beams to our van. They were between 2.5 and 7 meters long. And this is us transporting it to our van, which of course is only 3.5 meters long. So what do we do with the 7-meter-long beams? Well, we stored them, Materium stored them, and then brought it to us on campus later on. But this shows us that transport and storage is really a challenge in the world of reuse. And we should really try to align as much as possible the time you disassemble a building with the time that you reuse the building materials in a new construction. And that's why the work that I showed before, the prediction, the scanning, all of the preparatory work is so important. So once we had the beams, we also scanned them with a metal detector to remove any foreign objects that could damage our machines that we use for reprocessing the beams. We also planed the beams so that we could remove any surplus. And so throughout all of this process, I thought this was very fun to do with the students, but could we also use robots or some kind of digital fabrication to disassemble a building. And I talked a lot with my colleagues from the NCCR on DFAB. And while, I mean, we have this beautiful gantry robot at ETH, and that is a very good machine to robotically assemble digitally fabricated structures on site, in the workshop. But it's much more challenging to bring a robot to a site that is dirty, that is unstandardized, that is cluttered, and that is a lot of heavy objects to lift. And that's basically the definition of a deconstruction or demolition site. So we need some improvement still in the field of robotics, and that's also what we're discussing with the NCCR and DFAB to see where it could be useful in the disassembly process. However, there are companies such as Zen Robotics that use robots and AI to detect in complex construction waste environments how to sort materials for recycling. So here, of course, it's about construction waste. It's hard to reuse them, but at least they do this for recycling. But I think it's not so far-fetched to imagine a future in which we could use robots also to help us with reuse. All right, so the next step after disassembly, we have all of these materials. We need to distribute them, right, to the new construction sites. We need to do that as efficiently as possible. So we need a good tracking, tracing, and trading method throughout the element's different life cycles. So we reused the timber elements that you saw earlier and reprocessed them to make this dome. And on each of those elements, we engraved QR codes, as you can see here. And when you scan the QR codes, they lead you to a database that one of my PhD students developed, and he's doing a lot of research also on how to maintain and store data throughout time, because building life cycles are really long, right? Usually buildings get demolished maybe 20 or 50 years from now, and that's when we need to know which materials are in the building so that we can reuse them. So once you scan the QR code, it gives you information about the component, like this. It gives you information about where the component has been before, where it is now, what the dimensions are, what the wood type is, for example, here, what the condition is of the materials. It gives you also information about all of the other components of that same type in the building. It gives you also information about the other types of components in the building. So this is really what we call a material passport of the building. It has a passport of all of the materials that are in the building and how much of all of these materials are there and what they've been through throughout their lives. And that's really interesting because once a building gets demolished or renovated, we know exactly what materials are in the building and how much and in what condition and what they've been through throughout their lives. And that's really the kind of data that we need to reuse those materials. We work together with Madaster and Conquilor and other companies where we try to ask them how to implement that into the construction market already today. Now, I mentioned QR codes. QR codes are the choice that we made for our dome because we want everyone to walk by to be able to scan the QR codes with their smartphones and then have the information about it. But we can really use different labeling systems, going from barcodes to RFID chips, radio frequency identification chips. And the advantage of RFID is that it doesn't have to be visually available. We can scan it through other layers as well, which makes sense for the construction industry. But then you need a special equipment to scan it. You don't scan it usually with your phone. So there's advantages and disadvantages of all of those labeling techniques. But the point is, once you have these ways of tracking materials, you can link them to a digital twin, and you can also link them to each other, right? You can use the Internet of Things to connect all of those materials to each other, and then also help you with predicting maintenance, refurbishment, and replacement needs. Now, the construction industry has regularly been cited as one of the most fragmented sectors. And blockchain technology could potentially help us connect the supply chain through transparency and traceability. So blockchain technology can give transparency into where the materials are, and also traceability where the materials have been. For example, Tata Steel uses blockchain to trace things like CO2 emissions or product conditions or change of ownership and so on of their steel beams. So they give each steel beam a unique ID or material passport, and this goes from raw materials to in use to reuse and recycling. And this every beam is then tracked through this unique ID in a blockchain system. So with these tracking and tracing devices and the link to the digital twins, we have possibilities to also talk about the materials online, to trade them, and so on. And so what we want to do is matching people who have materials available for reuse, someone who is disassembling a building, with people who want to reuse those materials in their new design. We want to create a matchmaking service for reuse components. A Tinder for reuse, basically. So companies such as Access Materials Exchange Platform are already evaluating blockchain technologies and AI and so on to do so. All right, last but not least, we have to completely change the way we look at design and fabrication of our buildings. We need to design with what we have, with the available stock of materials. Now, this is work with MIT that we did on applying computational design algorithms on an available stock of materials, these timber beams from this timber-framed house, and we designed some geodesic domes with it. And here you see the inventory of beams that we got from the building in Geneva. So we thought, well, we have some timber beams here, so let's actually build the dome. So we discussed different design choices that you can parameter and in the computational design algorithm in order to make choices for our dome. So for example, we don't want to use the 7-meter long beams, but we want to privilege using the shorter beams for the dome. We also want to minimize waste. So here you see the white part is the waste elements of our dome, the beams in Geneva that we use for the dome. And we made some furniture like this with those waste elements to sit in the dome, because actually the dome was built in the Bauhalle, and we realized some people used it for their lunch break after a while because some people put some tables in there, and so we could also put some furniture for them to sit on. It's always nice to see that your projects are being used and being useful for society. All right, so are you ready to see what a pipe can become when it's not a pipe? All right, it can become a connector. It became a connector in our dome project. So really, the reclaimed pipes from Geneva became the connectors for our greenhouse dome, but it has not always looked this beautiful. We first had to test a bit the strength of this connector because it's a pipe, we have no information about it, it's just reused materials. And we realized very soon that we needed to strengthen these connections and also aesthetically finish them. So while part of our team was assembling the dome, the other part was applying computer numerical control, or CNC milling, to the OSB boards that we had left from Geneva to make these round shapes into the OSB plates to fit right into the pipes. So this would have been impossible to do without digital fabrication because we needed the speed, we needed the precision, we needed to adapt this to the pipes that we had found in the building we disassembled. So here you see it's not about really using robots all the time for everything, but here it's actually very useful to use digital fabrication techniques. So this finished off the structure of our dome, showing that a pipe can become a connector, like a caterpillar can become a butterfly. So I'm happy to say that the dome will become a circular hub, then an outside meeting space for a city hall, and finally a greenhouse. Now, maybe some of you know about the summer course that I'm going to give this summer at ETH, where we're going to go through all of this process again of digitalization at each step. And we're going to build also a dome on campus, which will be there for the entire summer for you to come and see. And lots of students are quite excited about this very hands-on experience as well of digitalization for circularity. So I want to conclude my lecture with this quote of Buckminster Fuller, who is a famous futuristic inventor and the popularizer of the geodesic dome. So he said, you never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete. So we clearly need to change the current linear model that is polluting, that is depleting our resources, that is generating waste. But we'll only be able to do this if we can show that the circular model is competitive enough, is faster, is better, is cheaper, is just the most common sense thing to do. And I strongly believe that we need to explore digital innovations to get us there. And that is what the Circular Engineering for Architecture Lab is all about. Now, if you need to take home one message, is that if we want to make buildings part of the solution, then rather than part of the problem, then you need to treat building components like you were treating your Legos when you were little. You need to give them multiple lives. Now, feel free to scan this QR code, which will bring you to our CEA Lab website and also our social media links, so that you can follow our work throughout what we do in the next few years. And of course, I want to finish this lecture by thanking my team, the CEA Lab members, because without them, all of the work that I presented today would have not been possible. They've done such hard work, and they're such talented, intelligent, passionate, driven, and kind-hearted people. So thank you very much to the CEA Lab people. I also would like to thank EB for warmly welcoming me at ETH. I would like to thank also my colleagues from D-BAUG, from DMAFT, from D-ARC, and from the other departments, because my research is inherently interdisciplinary, so I really need your support and your expertise for me to achieve or pursue my mission. I would also like to thank ETH, and in particular the president, Joël Mézot, for giving me this huge opportunity, this incredible opportunity to explore the circular construction industry. I would like to thank also my colleagues at EMPA, in particular Peter Richner and Christina Ore-Hunig, for inviting me as a guest professor at EMPA and enabling me to exchange so much with nest explorers and so on. I also would like to thank my mentors at ETH, Guillaume Habert and Robert Flatt, for their wonderful guidance throughout this new professorship. I also would like to thank my previous mentors, Paul Chen, Corentin Fivet, John Oxendorf, Niels de Temmerman, and Christelle de Mittenare, for continuously inspiring me and encouraging me throughout my career. And finally, I would like to thank also my family for their love and support, and especially Nicolas, my partner, who followed me to this beautiful country full of lakes and mountains and cheese fondues, and enabling me to fulfill my wildest career dreams. Thank you very much also to all of you who came today in person, despite COVID. Thank you also to all of you who are listening in online, thanks to the live streaming. Thank you very much for your kind attention.